my personal dream was to do better than Planck. How do we go beyond Planck? How do we keep exploring the universe with the CMB? And working on the SPT data is one of the ways we can actually do this. Okay, so what the CMB is, for those of you who work on completely different topics, the CMB is this light coming from the last Kepler surface at redshift of about 1100. And what's so special about this epoch is that before the universe was completely ionized, we had electrons and photons that were strictly coupled through Thomson scattering. And so photons were just not free to propagate long distances in the universe. The universe was opaque to photons. So we cannot really receive light from these earlier epochs. And then what happens when the universe cools down at a temperature of about 3000 Kelvin is that protons and electrons recombine into neutral hydrogen. And for the first time in the history of the universe, the photons are free to propagate very long distances. So long that today we receive this radiation that has a black body spectrum with an average temperature of about 2.7 Kelvin. But it also has small differences of temperature in different parts of the sky. And the correlations between these different points actually contain all this amazing cosmological information about the whole history of the universe. The CMB encodes information about the initial conditions of the universe set, for example, by inflation, all the beautiful physics of this primordial plasma, the physics of recombination, but also all the interactions that these CMB photons had later on in their propagation through the universe. So, for example, some of the CMB photons interacted again with free electrons when the first stars reionized the universe, and also they get distorted by gravitational lensing from the large-scale structure of the universe. So it's an incredibly rich data set that we can use to study the universe. And the way we usually study this, so essentially these CMB anisotropies are distributed as a Gaussian one field. So there are two numbers that we care about, or two sets of numbers. One is the average of this Gaussian, and the other one is the variance, or the covariance. And so what we usually do is that we don't work in real space, we work in spherical harmonic space. We decompose these maps into spherical harmonics, which is just a Fourier transform from the sphere. We take the coefficients of this spherical harmonic transformation and we calculate these variance. And this is the power spectrum. So it's the power spectrum that we see all the time when we talk about the CMB. This is, for example, the power spectrum from Planck. It's not exactly this is CL quantity, it's a CL multiplied by the multiples squared. This is the multiple, so at large multiples you have small scales, and at large multiples you have, at small multiples you have large scales. What's interesting about the CMB is not only you have anisotropies in temperature, also 10% of the CMB photons are polarized. This is because Thomson scattering between electrons and photons in the presence of a local temperature quadrupole can produce linearly polarized light. And the source of these quadrupoles can be multiple, essentially scalar sources, such as density perturbations, produce a very distinctive path, which are the E-mode polarization, this kind of path. P-rotational, and then you have tensor kind of sources like primordial gravitational waves that can produce both E modes and B modes. You can again study these patterns through angular power spectra, and so you can have, the usually angular power spectra that people look at for CMB. This one is for temperature, TT, EE is the E mode power spectrum, BB is for B modes. And then you can also study the cross correlation between temperature and polarization. And the final piece of the puzzle that I want to give you, the final observable that I want to describe is gravitational lensing, because this has become really an incredible source of information in the past 10 years, thanks to Planck that provided the first full-sky map of CMB lensing. And CMB lensing introduces different effects in the CMB, but one of them is to introduce a non-Gaussian signal at the level of the four-point polarization function. You can actually measure this signal in order to reconstruct the lensing potential of this large-scale structure that distorts the CMB path. And so this is an example. This is again from Planck of this lensing power spectrum. And we also fit for this when estimating cosmological parameters from CMB data. Okay, and my final slide of this introduction is about how do we go from these power spectra to parameters. Well, we have different models. One of the models is the standard model of cosmology, lambda CDM, which is based on the validity, essentially, of general relativity to describe gravity, the standard model of particles to describe interactions between particles, and it assumes the existence of cosmological constant for dark energy and cold dark matter. And with only 6 parameters, essentially, you can fit all of this beautiful data from the CMB. You have a couple of parameters for the initial conditions of the universe, one parameter that describes when reionization happened, one parameter that describes, essentially is linked to how far the last scattering surface is from us. And then a couple of parameters that describe the energy content of the universe, in particular the content of ordinary matter, so baryons in cosmology slang, and the physical density of dark matter. But what's very important is that you can also extend this standard model of cosmology. And for example, if you change the number of neutrinos that there are around, the kind of interactions between different particles and so on, it will have an effect on the CMB. And since the CMB physics is particularly easy to describe, the CMB is really a laboratory to constrain fundamental physics in a relatively easy way. That's why it's so popular to actually do this job of constraining fundamental physics. So this was the outline, and then I'll leave the stage to Etienne to go into the meat of talk.
Thank you. Hello. So I will now present our maps and our beam powers with the subspot telescope. And so, as sorry? Yeah. Is it fine?
No, it's fine. It's fine.
So as you were saying, there is a lot of information that we can extract from the CMB, and it's particularly we can understand that from this plot. So here you have the signal to noise measurement of the power spectrum measured by Planck. This is TT temperature. This is input polarization EE across TE, and lensing just in terms of signal to noise. And that shape on the large scales shows that the Planck measurement is sample around limited. But then Planck had large models relative to what we do now, and so quite small resolution. So the signal to noise drops at the small scales. And what we see from that plot is that there are still a lot of scales that are unexplored in CMB, and so this is what we will target, and namely the E-mode polarization, where it's not sample balance limited on all scales. So we're really probing those scales just to try to answer some questions that we have. Mainly can we learn more about the universe. And so this is what we do with SPT. SPT is a ground-based experiment on the South Pole. It has a 10-meter primary edge, so it's 6 times larger than Planck. So you can achieve arc-minute scale angular resolution at those frequencies. And we have SPT-3G, which is our focal plane, with 16,000 detectors, polarization sensitive and high frequencies. If I recall correctly, Planck had only 52 detectors. So we're really holding small scales with low noise. Alright, so when you build a CMB experiment, you have two choices. Either you go wide in the sky and you do like Planck, and so this is a satellite-borne experiment. You look at 100% of the sky. The choice that we did was to go very deep, so low noise levels, but on a small scale fraction, which is that green patch here. It's the SPT-3G main field. So we are not only observing that field, we're also observing the yellow and the red fields, which are the center and white fields. But today we focus only on the green patch, which is our deep field. This is where we have the lowest noise levels. And ACDR6 went halfway with half of the sky and 3 times larger noise levels as SPT. So we observe that patch, we make maps out of those, and I will compare the maps from Planck, ACT, and SPT on that small patch here, 8 times 8 degrees. And so I start with temperatures, CMB temperature is this, and I think it's really a nice plot. You can really see the CMB in red and blue there. Those maps have been filtered just so that they are comparable to the SPT1. And first what we can see is that there is very low noise in Planck already, because Planck measurement is already signal dominated. If we look at that source, it's a point source on the sky, it's not CMB. The beam of Planck is quite large, because this shape is elevated. And when you move to ACT and SPT, you get higher resolution because we have larger primary mirrors. SPT actually has slightly better resolution. We can see a third source in that spot there. We not only see sources, but we also see clusters of galaxies, decrements. It's that blue patch in the center of that circle. It's a cluster of galaxies. Today we're not looking at sources, we're looking at semi-entropies, but I guess we're just trying to show the instrument resolution. And so where we are
just on the previous slide, there's more blue stuff in ACT than in Planck.
Yes, I think it's a resolution effect because there is a smoothing. So this is polarization, Planck Q and U maps. Inside there are mostly E modes, and as you can see, it's mostly noise. And this is when we go to ACT. So ACT has 3 times lower noise levels than Planck. So in Q, you can see that cross shapes, horizontal and vertical. That's typical of the Q, how we define it. And that this is U, which is 45 degrees rotated, so X is there. You can still see some noise on the bottom of that map. Those are the SPT maps. So as you can see, it's less noisy, 3 times less noise. And there is another feature that I want to emphasize, which is that in the SPT maps, you do not see the horizontal stripes. We lose those horizontal modes. That's because of the way we make the maps.
What are the vertical stripes on the left?
Oh, it's still Q. It's Q. It's a cosmological signal. But we expect to have crosses, and but we remove just the horizontal stripes of the crosses, so we have only vertical stripes. And so the SPT maps are the deepest maps used in SPT analysis. Here I'm showing the noise power spectrum compared to the signal power spectrum in gray. And so for EE, the co-added noise level, so the co-add of the 3 frequencies is in red. And so we are signal dominating in baryon until L of 3500. We're signal dominating in temperature all the way. The large scale noise is coming from atmosphere. Alright, so we use those maps to make band powers. Band powers are just what we call our power spectrum. This is what I'm showing there. There are a few technicalities that we implemented here at IIT. Eric worked a lot on transfer functions, and I did some work on beam modeling and painting. So how we go from those maps to band powers. And as we analyze band powers, we keep them blind. So we do not want to bias ourselves towards the previous results. So we keep the data blind until we pass a series of tests. And we have, for instance, map null test which means so we're trying to look for systematic effect in our data, and so we separate the data in two halves in such a way that we're sensitive to a systematic effect, and we take the difference of those two maps. So for instance, here I'm taking all the data that was taken when the telescope was going to the left, and all the data when the telescope was going to the right, make a map out of those, and we check that the power spectrum of that is consistent with 0. Actually, in that specific case, it's not. You can see that noise line there. It's that sharp peak that comes from the detector's noise line. So we had to cut that. But modulo some cuts and some rearrangements, or we pass all of our map null tests. And we have another set of null tests, which is at the band power level. We compare the band powers that we have at a given frequency, say 150, 150, cross autocorrection of 150 maps. And we compare it, for instance, with 95, 150. We have a series of them, we have plenty of them. And we check that this is consistent with 0. So we have map null test, band power null test, but also a later parameter null test. And our data pass all of our null tests after some time. And so now I'm going to show you the band powers. So I start from the state-of-the-art measurement of Planck in green. So the large scales are very well measured by Planck. And AXIA6 also provided a very nice measurement of TT and TE. Here it's a zoom in of TE, just changing the Y scale so that we can see the details. And here are our measurements made at IIP of the SPT-3G D1 T&E powers. We don't probe the large scales because we only have a small scale fraction, but we have very high resolution, so we can really measure the small scales of the CMB here. We cut the temperature at 3000 so that we don't have to model astrophysical formation. And as you can see, and this is really what we wanted to achieve, we have a very nice small scale measurement of TE and EE in polarization, and this is where we get some information. And so in order to compare those data points, it's better understood in terms of signal to noise. So there's still this competition between sky fraction and noise. And so for instance, this is the signal to noise of the measurement of TT by Planck, ACT, and SPT. So Planck has much more sky, so better signal to noise in temperature. But we have better resolution, better noise. So ACT has even more sky than us, so has better signal to noise in all temperature, because all measurements are signal dominated there. But in TE and EE, you can see that we dominate on the small scales, and so we provide the tightest band power measurement of TE at L above +200 and EE L above 1800. And I think it's quite interesting there because we have 3 different experiments measuring EE, and so the peak of the sensitivity is not the same scale, so we provide complementary information, but we also have significant overlap, so we can perform some cross-checks of each of the data and try to find systematic effects. So those were the band powers. Now we move to lambda CMB results from only this TT and EE data. So we have band powers, we want to measure cosmological parameters. We do very standard Gaussian likelihood, where we compare the data to the model prediction that we obtain with pulse mass solvers or emulators. There are also a bunch of data modeling there, so foreground emission and systematic modeling that goes in there. And I spent my PhD computing that covariance matrix there because we really want that to be accurate. And all of that is implemented into this differentiable Python-based likelihood framework created by Lennart. That's very handy. All right, so we use that likelihood. We build that. We keep our data blind, then we check that we are unbiased. We do that using simulations. We have 100 end-to-end simulations, and we verify that we recover the input parameters. It's quite an expensive run to do all of the simulations. But also we were worried that our pipeline could bias any cosmology towards Planck because it has some pieces that come from Planck simulations. So we check that on 10 simulations with an anti-bias cosmology, we actually recover the anti-bias cosmology. As I was saying, we also perform a set of parameter null tests. So we were still tracking down systematic effects in our data. So we take each of our systematic effects can have a frequency dependent shape. So we take the difference between multiple frequencies, and and we check that the recovered parameters are all consistent, assuming lambda scale. So we do that blind, but here you can already see the mean value, but we perform that blind before and blind. So we pass all of those null tests, then we commit to report the results, but we still change our analysis after unblinding. And so this is why what I want to highlight now. We added two components to our data model after unblinding. One of them is quadruple Orr leakage. It means that in our polarization maps, we have copies of the second derivative of temperature. And we really can see that when we stack point sources because it provides a typical shape in the data here, and we can model it. And then we propagate it down our pipeline. That we had forgot to include. And then we relaxed our assumption that the beams are the same in polarization and temperature. And this helped us improve our large-scale E-mode consistency on the very large scales. So those effects, we added them after unblinding, where we find evidence that they are not cosmologically dependent, and we believe that they provide a much better understanding of data. So we add them after unblinding. And so now I can show you the results. Lambda CM is very quickly to our data. So on the right, you have the band powers in TT, T&E of each of the frequency channels. And so the fit, the line is the lambda CM fit plus 4 rounds. And so for instance, you can see that the residuals are all very good. The chi-square of the fit is given there. It's a T of 50%. And from this data, we can only fit, for instance, temperature. This is what we get. We get a measurement H0, omega D, omega C, and S. This is really the parameter that we are sensitive to. I'm at EE. So as you can see, there are more information in our EE channel than in our TT channel. Then we have TE. Those measurements are almost all independent. And so we combine them together. This is TE and EE. I want to show that because we were really looking for polarization signal with this analysis. And also these contours are almost foreground free, so they are not dependent on the foreground model. And then in dark it's TT, TE, and EE all together. You can see it's almost the same as TE. So those are our main results. And what we also checked is that our measurements of lambda CM does not depend on scale. So we have band powers between 400 and 4000. And so we split our data into 3 parts. Trying to answer the question, is lambda CM consistent across scales? And this is what we find. So if we compare H0 from measured by each of the subsets, it's always consistent with the mean value, and they are consistent with each other. So we have this new data set, which is TTTE, and we verify that it passed all null tests. It's consistent in TTTE, the lambda CM measurement is consistent in TTTE, and it's consistent with scales. But later we will add new information, so it's SPT lensing and other CD data sets. So now we will leave it to Ali, that will show you those combinations.
Questions at the end, right?
Yes.
Okay, hello everyone. So I'm going to continue showing you our results from SPT, starting first briefly with what are the lensing measurements that we produce from SPT. This is a work that was led by Fede and Marcus Leia from our collaboration. We use the polarization maps that Etienne showed at the beginning to reconstruct the lensing band powers from the lensing data. And we can see here that these band powers are agreeing well with the predictions of lambda CDM, either starting from the Planck measure inferences or from SPT. What we also find is that these lensing measurements are actually the most precise at multiples above 350 at small scales compared to other experiments that produce such lensing measurements, with a signal-to-noise ratio that is given by the order of 38 sigma, which is an immense improvement on these measurements and will allow us to improve our constraints even further. So now on to the LSDM constraints from the CMB. We need some definitions for you not to get too lost at this point for the different terminologies. So the different data sets that we consider first is what we call SPT-3G D1, is the word that we are presenting today, that includes polarization and temperature and the lensing band powers that you just saw. We define a Planck likelihood that combines the multi-Cosmo temperature and high multi-Cosmo polarization and the lensing band powers from Planck. When we put SPT and ACT together, we define this to be SPT plus ACT, that includes temperature, polarization, and also the lensing from both experiments. And then putting all three experiments together, we call this CMB SPA in temperature, polarization, and lensing. We also impose a prior on the optical depth to polarization that Silvia introduced at the beginning, instead of using large-scale information from Planck. Also, just to some definitions on the parameters that you're going to see, we already saw H0, the expression made today. We have a method density parameter that we call omega m, which is the method density relative to the total energy density today. We look also at one particular parameter that we call sigma 8, which is the root mean square of matter fluctuations on a sphere of 8 megaparsecs. That is important for the clustering of matter that we will see later. And then there's a fourth parameter that is RD, which is the sound horizon at the end of hydrogen recombination. That is also an important parameter to look at, especially when comparing BAO. Our first result is that SPT alone is able to provide constraints and some cosmological parameters that are very close to those of Planck. And this is just coming from 4% of the sky. Thanks to our high resolution, this allows us to achieve such a precision. And you can see, for example, on H0 how we have the error of 0.6 compared to the one from Planck at 0.49. And the agreement between SPT and Planck is at 0.4 sigma, which is also a very good agreement. We also compare our results to ACT, which also shows that our results are very consistent with those and very similar in the constraint power on cosmological parameters, even surpassing them in some cases, for example, here in omega n, where we also find that the consistency between SPT and ACT is at the 1.1 sigma. Having these three experiments agreeing with each other is an important achievement for CMB. It shows you how robust CMB science is. It is invariant undergoing from one experiment to another. We always have very similar results. It also shows you how it's an important test for the lambdas in the N model, given that all the three experiments are able to agree with its predictions. And now, once we have this agreement between the experiments, we can also look at another important conclusion, which is that ground-based experiments are now reaching a stage where they can provide constraints on cosmological parameters that can surpass that coming from Planck. For almost 13 years, we've had Planck dominating the world of cosmological constraints, and now we are entering a new era where this can be achieved not only from the space but also from ground. And just as an example, you can see how the constraint on sigma 8 from SPT plus ACT is around 18% better than the one coming from Planck alone. And then the combination of all three experiments, SPT, ACT, and Planck, gives you the most precise constraints on cosmological parameters, particularly on SDM, coming from a single probe, the CMB. And this is also a fascinating achievement where now we have, for example, the constraint on H0 is around 30% more than the one coming from Planck alone. Having this agreement and this high precision, we can make new statements about important aspects of our model. For example, we can say that the clustering of matter parameters that are parameterized by sigma 8 and omega n are showing a great agreement between different probes of the universe, probes that range in different epochs of the evolution of the universe. Either from the CMB lensing, from weak lensing cross-correlated with galaxy clusters, from primary CMB data, or from weak lensing alone. You can see how they are all agreeing with each other in this plane, and this is another immense achievement for the lambda CDM, for the concordance model. Note again that the constraint on sigma 8 coming from SPT alone is very comparable to the one coming from Planck, and this is another hint that we are really achieving a very good precision in our data from SPT. Another important problem that we are facing nowadays is the Hubble tension that Silvia mentioned at the beginning. Basically, this discrepancy between the inferred value of the expansion rate today coming from local universe measurements, what is used by distance ladder techniques, and the one coming from the CMB in particular, under the assumption of a cosmological model. And you can see how this discrepancy has been evolving over the years and increasing as more precise data is being presented from the CMB side as well as from the local universe side. And by tension, I mean that there's anything that has a discrepancy between these two values that is more than 3 sigma. And naturally, when physicists face a problem, they want to find a solution, and they propose theoretical models for these solutions. And but before going into that, this Hubble tension now is being confirmed by 3 independent, almost completely independent experiments, SPT, ACT, and Planck. And it is now at more than 6 sigma level. From SPT alone, we have it at 6.2 sigma, SPT plus ACT at 6.8, and from the combination of the 3 at 6.4, when compared to the latest choose inferences of H0. And a few years ago, with Silvia and Karim, we looked at several models that have been proposed to solve this tension, and we found 2 in particular that are very promising in reducing the tension below the 3 sigma. One is called the varying electron mass in a state with spatial curvature, and another one is called early dark energy model. And we looked at several statistics to quantify how well these models are able to actually solve the problem. What we found is that indeed these 2 models in particular are able to reduce the tension below the 3 sigma level, but we do not find a strong preference of them over lambda CDM. And so the best thing we can say at this stage is that we need more data in order to better assess these models. Finally, for the lambda CDM extensions that we revisited in our work, we do not find from the CMB alone any statistically significant deviation from lambda CDM. And just as an example, I'm looking here at the presence of additional light particles that is quantified by this parameter and effective, that can, to see whether we are indeed having any additional problems, any additional particles compared to the predictions of the standard model, or to any variations in the paramodial helium fraction. From SPT alone, we find that the constraint on unaffected is around 30% looser than the one coming from ACT, but their combination provides an 11% tighter constraint on this parameter compared to Planck alone. And what we see is that all the experiments are agreeing with each other and with the predictions of the standard model on this parameter, either when it's varied alone or when it's varied in combination with the helium fraction of P. Where we can see that, again, they are all agreeing with each other, and with the predictions of the standard model, as well as with the measurements that are coming from metal-poor galaxies on this parameter. This has been just from the CMB, but now Lennart will show how things will change when combined with BAO, and will show also some additional results from SPT.
Okay, thanks everyone. As I lead us walk you through the cosmological results when we consider cosmic microwave background data, I will now combine our and other CMB data together with baryon acoustic oscillation data. But maybe for the non-cosmologists in the audience, a very quick introduction to baryon acoustic oscillations, or BAO. If we imagine we have the CMB at very high redshift in the very early universe, what we see here are the seeds for structure formation. Well, these then evolve into the large-scale structure that we observe in the universe today. So by that I mean galaxies and large clusters of galaxies and filaments and so forth. And indeed, we can trace this evolution. We can find the characteristic scales that we observed in the CMB represented again in the large-scale structures, characteristic distances that we see galaxies like to be from one another. And so a little bit like shown in the cartoon here, we can trace this evolution, and so the baryon acoustic oscillations give you a tracer of the matter clustering, the matter density of the universe throughout cosmic history. So this makes for a very powerful cosmological approach, certainly in combination with the CMB, where you have a high level anchor in the early universe, and then multiple measurements in the local, more local universe with respect to the CMB at least, that you can compare your predictions to. So BAO is not a new probe that can many measurements realized, and of course here the IIT is intimately involved in the Euclid satellite mission that will measure this to exquisite precision But while we wait for Euclid colleagues to bless us with their data, we use data from the ground-based experiment with dark energy spectroscopic survey, the DESI instrument, which has also done a nice measurement of the BAO piece and released their latest data release, DR2, just earlier this year. Before we can go ahead and combine the BAO data from DESI with our CMB data, we better make sure that the two are consistent. So how do we do that? Well, the BAO data constrain the matter density, omega m, as well as the combination of the expansion rate and the size of the sound horizon at the end of the baryon graph called HRD parameters that Ali kindly introduced you before. So what we do is we look at constraints in this two-dimensional plane. DESI one is shown in grey and the SPT1 CI indicated in blue. Now the two contours are further apart than 3 sigma in this 2D space. We say that we have an inconsistency. If they're less than 3 sigma away, we say, okay, this looks like the same story. We can combine the data set and we report the associated joint constraints in the paper. So for SPT and DESI, this comparison comes out at 2.5 sigma. It's on the high side, but it's under the threshold we set for ourselves. So this seems okay. If we look at other CMB data and sort of do a little stock take, this is the story that we see. It all sort of comes out around our 3 sigma threshold. In particular, the comparison of our CMB SPA dataset that contains SPT, Planck, and ACT, we're at 2.8 sigma with respect to DESI, just underneath the 3 sigma threshold. So what do we make of that? Well, to me, Ali demonstrated to you that the CMB data coming from SPT, Planck, and ACT, 3 nearly independent experiments, is extremely consistent across temperature, polarization, angular scales. It tells the same story. And so I'm inclined to think that this is the closest from the CMB side we have to the truth. Now naturally then some subsets of that will fluctuate above the 3 sigma threshold, underneath this threshold that we've set for ourselves. While we have this difference though that is around this 3 sigma value, we should be quite careful about interpreting joint constraints that come from CMB and BAO data. Otherwise we suffer projection effects, and certainly already in lambda CDM we get some interesting or fearful implications for inflation that we might want to take with a grain of salt for now. The interesting part though is that these differences that we see in the standard model, they can be reduced if we made to go away completely when we consider extensions to the standard model. So if we allow for new physics, we can accommodate these 2 types of data sets better. This happens by projecting these differences onto the extension parameters that you introduce. And so you end up translating your 3 sigma tension into a 2 to 3 sigma preference for new physics. And this is not unique to one model or one class of models. We tested quite different ones in the paper, along with early depth energy in Ali's follow-up paper. You can see the different classes of models I've written down here. For each of them, on the horizontal axis, you see how much this model is preferred over the standard model. If we only consider CMB data alone, those are the dark grey bars. Everything's below 2 sigma. There's nothing to see here from the CMB side, as Ali said. But when we add DESI, we go to the light blue bars. All the preferences are increased, and in some cases above this magical 3 sigma threshold that we set for ourselves. In particular, the 2 models that Ali highlighted, baryon spectral curvature and electron mass, or as early depth energy, succeed in raising H0 while you add it as well. We dissect these constraints in the paper, walk you through what happens at the parameter level to give rise to these effects and tie to the underlying physics. I won't go into the details here, but what do we make of all of this? Well, the way I see it for now, we don't have definitive evidence for a breakdown of lambda CDM, at least not yet. First and foremost, the statistical evidence remains moderate. It's at the 3 sigma level. It's not deeply convincing, certainly for tossing a model in the bin that's performed extremely well over the last decades. We also haven't seen a detection or preference for one of these models really from either probe alone, CMB or BAO data. This may not happen. Perhaps we need to combine precision to tease out these hints, but for some of these models you could imagine that being the case. Of course, we also want to be careful. There may always be systematic effects present that we haven't accounted for. passes as a caveat. At the end of the day, though, more data will allow us to clear this picture up, either by just beating down the statistics and shrinking my error bars, seeing if this persists or not, but also as a valuable reference point to handle any potential systematic effects. So more CMB data will be helpful, but of course also usually error measurements as well as other cosmological data sets. If you disagree with any of these conclusions, or you're upset because we haven't considered your favorite cosmological model, fear not. Everything you need to carry out your own cosmological analysis with this data is public, along with tutorials and templates to help you get started running these things. Before you go ahead and perform big MCMC analysis, do check though if they're not already public, or the chains that at least so painfully ran can be found on Lambda, so no need to set infinity on fire. So far we've talked about these band powers that Etienne has produced in temperature and EMO polarization. For a couple of slides now, I will transition to talking about another power spectrum measurement that's based on the same 2 years of data collected on the same 4% of the sky observed by SPT-3G. But this one concerns V-mode polarization, so the spiral polarization pattern that Silvia introduced at the start. This measurement was carried out by Etienne at the University of Chicago. It targets the large angular scale V-mode anisotropies. This is a somewhat unusual analysis for an instrument like SPT-3G. Typically, small aperture telescopes are used for this, but there's a proof of concept analysis that demonstrates that actually large-scale V-mode searches can be carried out with big telescopes such as SPT as well. Along the way, Jessica, along with collaborators notably Anna Curver, developed new analysis techniques, for example, to deal with polarized atmospheric signals. And so the analysis is a success, and as you can see in the plot behind me, she produced very nice band powers shown in red here that constrain the large angular scale V-mode polarization, and in turn can then be used to search for the signature of inflation, primordial gravitational waves. And just with the SPT data, we can place an upper limit on the tensor-to-scalar ratio of 0.25. But these data are not only interesting for inflation, plenty of new physics may live in the V-mode power spectrum. For example, anisotropic birefringence, so the differential rotation of the polarization of CMB photons across the sky is made, of course, for example, by axions, can be constrained with this. And indeed, the SPT-3G data are able to provide you the tightest constraints on the strength of this kind of anisotropic birefringence, and you only look at the V-mode power spectrum here. That's shown in the marginalized constraints that you can see in the plot here. It's simply an amplitude parameter of how much of this differential rotation we have, and the SPT-3G constraints are shown in orange and grey dotted line in 2 different setups. Okay, I'll leave things here and hand back to Silvia.
Okay. Yeah, so what's incredible about this data set is that it's only a small fraction of what we already have on the can and what we also plan to collect. The results that you've seen today are from only 16 months of observations. It's 2 years of observations during the Austral winter. We already observed for 5 full years, right? And we're going to observe for other 4 years. And not only these 4% of the sky that we use today, but we already observed these much larger patches. So we have the observations of these yellow regions, which are the summer fields, and the analysis of these fields are led by Federica Guidi, who was a postdoc until a few weeks ago here at IUP for 4 years, and now is going at the University of Davis in California. And then we also already observed these much wider patches of the sky in red, which we call the white fields, and the analysis is currently led by Etienne, who is a PhD student here, together with Shira Fitchman at the University of Chicago. So the reason why we are observing these larger patches of the sky is that what limits us is that we have our noise is so low that we are already limited by sample variance. So simply by the fact that we are observing small patch of the sky. We really need for this cosmological analysis to go to observe wider patches in order to have better constraints. And here I show the signal to noise in temperature and polarization, for example. When you, in green is what we just showed, so this is the signal to noise of the analysis that we just showed compared to Planck here. And these other two curves in orange and red show you what we are going to be able to do when we add these additional data sets. So there's a lot going on, a lot of analyses that are going on. Very soon we are going to have a new analysis on gravitational lensing that will come out. The one that we used for the cosmological results that we've seen were based only on polarization. These new results will be based on temperature and polarization. Hopefully next year we will publish the analysis of the summer fields that Rida is leading, with three times more sky than what we showed today. And then in progress is the analysis of the white fields, co-led by Etienne, with 7 times more sky. And we have all of the cosmological forecasts for these data sets, and we actually expect to be able to set constraints on cosmological parameters which are twice better than Planck with SPT alone from the full surveys, and almost three times better than Planck when combined to Planck data. So in the future, we plan essentially to analyze not only these new fields, but I mean the full data set that we have. So for example, the main field will be observed for 9 years. What we've seen is only from 2 years. So we have a lot of more depth that will come with this data set. And that's not even all, because SPT-3G will observe until 2028. And from 2029, we have a new camera, which is called SPT-3G Plus, which will observe the sky with 7 times the mapping speed of SPT-3G, so it will be even more powerful. And the reason to do this is to improve the constraints and maybe discover and get the Nobel Prize on primordial gravitational waves. This is to combine the data of SPT-3G. Oh, yeah, I keep I didn't see it, but to do this, to combine the data from BICEP, which is a small aperture telescope, which is the world leader in setting constraints on primordial gravitational waves from inflation, as measured from CMB. We haven't detected yet. Combining this data with the SPT data, because essentially one of the limiting factors of this search right now is the fact that gravitational lensing produces non-primordial B modes that contaminate the signal. And you need large aperture telescopes as the one from SPT-3G that can clean this contamination from the BICEP data. So this is where we are today, at least the last result that was published, and we really expect that with SPT-3G and SPT-3G Plus, we will be able to do better by almost a factor of 10. So really we will lead the way in this quest of trying to figure out this puzzle of primordial gravitational waves. And with this, I will finish just summarizing some of the results. We've already seen how powerful this data is. It's only a fraction of the data that we have, and we are already entering a new phase of CMB science. We are doing better than Planck, combining with ground-based experiment, with ACT. on some cosmological parameters. I mean, the legacy of Planck is untouched because we're not going to do the large scales that Planck was able to measure. Some parameters are measured by Planck, and that's it. The optical depth realization is something that you can do only from large scales in polarization, and we're not going to get that again until a new satellite goes to space, although there are efforts from the ground, but it's very hard. So there's this huge legacy of Planck that remains, but we can do better by adding all of this information at small scales. We demonstrated how robust CMB science is. We have almost three almost independent experiments that give the same results. That's very powerful because we really can use these data sets to learn about the universe. And you've seen that there are interesting things. There's the Hubble tension. Maybe it's a sign of new physics that we don't understand yet. Maybe there is this new disagreement between BAO and CMB. Maybe again, new physics or systematics. Who knows? We need more data and more understanding. And I've shown you this is only the beginning for SPT, and we have the luck at IAP to be fully involved in this beautiful experiment. I just wanted to, in this talk, you've seen the shiny part, right? The cosmology, the fun part, the models, and so on. This was maybe 6 months of work to get these results. I mean, the real work was the 5 years that we spent in doing all of the pipeline, the tests. That is, when Etienne says we passed the no tests, yes, it's 2 years of our lives that we spent in understanding systematics. There is a lot of hidden work, hard work, that there is in analysis of that. Many brilliant people working on this, and maybe not showing the shiny parts. But really, without all of this work, with a lot of innovations and ideas, it's impossible to have these results. So really, the core of the work is often less fancy than showing just the progress. But it's thanks to this work that we can actually trust what we get out of this data. And with this, I thank you very much. Maybe you can go down here.
Great, congratulations for getting this far into all these standing and lovely results and wonderful. Can we go back to the super slide that Etienne showed, showing you the difference between the 3 experiments?
This is one.
No, the image.
Oh, the image, yes. The blue points we are not convinced about.
Yeah, so this is fantastic. So, but first of all, the question is, it looks to me, what scales is the cosmological signal coming from? Because it seems to me the main difference here is you can resolve small scales very well. Is there, because on intermediate scales everything looks the same, and on small scales is there a lot of information compared to those intermediate scales? Just for someone looking at images.
Yeah, I mean, the CMB signal peaks at 1 degree. I mean, so you're going to see that, the correlation function, but then there is still a lot of information that you would need to filter probably some of the large scales in order to appreciate how much better we do at the small scales. Also, this is temperature, so as Etienne showed, I mean, most of the information is already sample variance limited because the signal is strong. So going down in noise will not gain you so much on the scales that matter for CMB. Where you see really the gain in going deeper is polarization, which is what Etienne showed next. Right here, you really see the noise. This is noise because the CMB signal is much smaller.
Okay. And then just a quick question. There was a lot of noise about the DESI results showing you that W is not -1. Do you have some comment about that, and do you guys bring anything to that particular question?
It's important. It's important to note that the DESI data itself doesn't give you a strong preference for evolving dark energy not even above 2 sigma, I don't think it's 1.8. And then any CMB dataset you combine with will then tease out this preference, simply because you have a difference between what the CMB gives, feedback, ACT or SPT versus DESI, and this difference can be quite well absorbed by this evolving dimension model. But it's not the only one, as we've seen, there's different models that can also kind of do the same thing.
I just want to add that supernovae also play a crucial role in determining how much is this preference.
I mean, until we don't have independent experiments that confirm this, I mean, without combination of different, right? I mean, we need DESI alone, BAO alone, to give us a signal that is compatible with another probe that gives us the same signal, right? And right now we are not there.
So congratulations also from me, and it's wonderful. So I just came in 10 minutes ago, so you might have said it. Do SPT and ACT use the same foreground model as Planck, or do they build it themselves? After all, you have higher resolutions, but you don't have multiple bands. So it's difficult, right?
We do have.
Oh, you do have multiple bands.
We have 3.
Okay.
Strictly speaking, we're not using the same forward model. Each of the forward model has the same components. But we're not implementing them the same way. However, it has our measurement is dominated by polarization, which is mostly forward-free. So it has small impact on the data, and we show that if we vary the forward model, the impact stays the same. Well, the constraints stay the same. ACT is more sensitive to forward because they are probing the small scales of temperature and they're using them in the analysis. And so they have interesting results that using in their paper, namely TSE. But yeah, long story short, the results, the form model are mostly close.
Okay, thank you.
This is a question for Ali. You showed a model where there is electron masses varying in order to increase the value of the constant H naught. Is this variation compatible with the known bonds done from experiments in the lab and also from quasars on the variation of the fine structure constant?
So we did not look at the variation of the fine structure constant, particularly to salt Hubble tension. But from the CMB alone, you cannot make big conclusions about this model, because when what the electron mass does is changing the redshift of recombination, which will also change the distance from us to the scattering surface. And so you need information from the late universe in order to better constrain this model. And so when you combine the CMB and BAO data, for example, you end up with changes of 5 to 7% increase in the value of the electron mass that will result in the increase of H naught that can reduce the tension. But then if you want to include additional constraints coming from Big Bang interferences measurements, for example, that increase will diminish and it will not be as successful as actually solving the tension.
Thank you very much for this very combinatorial presentation. My question is, there has been a few proposals for new experiments to detect the deviation in the spectrum of the CMB, I mean energy spectrum of the CMB. Like Pixie and so on, which some of them are. Do you think that any ground-based observation can do the job, or if there is any new proposal or possibility for a satellite project?
Yeah, so I mean that's the big hope, right, for the CMB community is that sooner or later we will have a new satellite that can do spectral distortions. There are a few efforts from the ground. There's the Aspera experiment in India, and also in Italy they think about an experiment called Cosmo. It's extremely hard to do this from the ground, especially when you look for isotropic, like the average spectral distortion through the sky. The atmosphere is a big contaminant. There is a project in France to do a balloon, which is called Bisou, that might start to go deeper than the measurements that we have from Kobe. There's a proposal that passed the first phase now of the I think it was N8 missions at ESA called Fossil, which will be launched in 2040. And also spectral distortions were selected as one of the two themes for Voyage 2050, so for a large probe mission at ESA in the 2050s. Now the problem with that, right, is that these spectral distortions are expected to be quite small, so we would really need to measure primordial spectral distortions that we expect in lambda CDM. You would need to really an large probe from ESA satellite to detect that, and even then it would be like a few sigma detection, right? So you wouldn't need. It would be important to verify a series of things, but then to do cosmology from that, and we would need even more, right? So it's a long path, and we're not going to get there if we don't have all of these intermediate steps before. So yes, it's a hot topic in CMB science, certainly.
I have maybe a naive question, but you talk about the Hubble tension solution with the NE plus sigma k, but what's exactly the solution to Hubble tension? Is it a way to say this one is right, or the other is and the other is false? Or is it a way to try to match the two results?
Sorry, I didn't understand. Can you please repeat?
You try to find a solution to Hubble tension, but what do you try to do? You try to say this one is the right solution, or the other is the right, or do you try to match the two results?
So the way we assess whether a model can actually solve the tension is by looking at several statistics. These are quantities that tell you how much the value of H0 got closer to the one that is coming from shoes, and another quantities that quantify how much the model is able to fit the data by computing what we call the best fit chi-squared. And there are two of these quantities from the best fit chi-squared that we use to evaluate the model. And the criteria to say that this model actually solves the tension is not only to reduce the discrepancy in H0 when comparing the one coming from the CMB compared to the one coming from shoes, but also to see whether the improves in fitting the data that is coming from this model compared to lambda CDM, because our standard is always lambda CDM, given this is the model that we know so far. We want to see how much the improvement in fit to the data of this model is better compared to lambda CDM. And so far we don't have any of these models that have been considered to actually provide a much stronger preference over lambda CDM.
I think, just to complete Ali's answer, what we try to do is to change the H0 from the CMB, because the H0 from the CMB is model dependent. So it's this value if you assume lambda CDM. If you assume extended models, so it can be a different value. So the idea is what the supernovae are right, that's the actual expansional rate of the universe, and the value that you infer from the CMB needs to be changed by changing the model, because it's an indefinite measurement.
Okay, well, thank you very much. Thank you for this really nice presentation. I guess we can probably call this a day. It's really nice. So, a big applause.